So Anton, I think I will second what you just said. I think black holes are relatively simple. You know, they have only 3 parameters that are important. So plasma astrophysics is much more complicated, and find it very interesting. But one of the interesting products that comes out of black holes are, as Anton said, are relativistic jets, and we see these jets a lot in many objects in space. And I want to tell you a little bit about, let's say, how the basic properties of these jets. And one of the most important properties of these jets is that they are relativistic. That's why they're called relativistic jets. So I will focus most of all of my talk actually on the relativistic properties of these jets and how do they know actually that they are relativistic. So as I said, they are common in many systems that involve the compact objects. And for example, they appear in extragalactic AGNs, active galactic nuclei, if you heard about them. These jets that are coming out of these galaxies are huge. They are, the size of these things come to a distance of about, this is something like 10 million light years. It's 4 times the distance between us and the Andromeda galaxy. Okay, this is the size of these jets, and this is just a single galaxy that is emitting them, and they actually originate from the black hole within the center of this galaxy. So this is a very huge beast. Inside galaxies, you learned yesterday about these things that are known as TDE, tidal disruption events, when a star is circulating around the black hole and is getting ripped apart because of the gravitational tidal forces. Sometimes the matter that is accreted onto the black hole results in the launching of a powerful jets. And we see these indications for these jets. And there are also jets in stellar size objects. For example, in microquasars, X-ray binaries that I understand that you heard about them also emit jets. These jets are much smaller. The size of these jets is, I don't know, something like 1/10 of a light year, if you want. And the final object, these are gamma ray bursts. I believe they heard a little bit about gamma ray burst. Okay, gamma ray burst is an object that is produced from the death of a massive star. The inner part of the star is collapsing. It forms a black hole. Matter is accreted onto that black hole, and again, we have a black hole, we have an accretion disk, and one of the results of this is the launching of the jets. So I will focus this talk about jets of gamma ray bursts and jets of AGNs. So this is how a gamma ray burst look like. You see, unlike these huge jets that spread, these huge loads that we can see on the side, a gamma ray burst, we don't see any indication, any direct indication that we're actually seeing a jet. And all we see is like a blip in the sky that lasts for, I don't know, 10, maybe 100 seconds. It emits a huge amount of energy, and then it quiets down. And from this small blip, we can deduce a lot of energy, a lot of information. And I will address why we think that this is a jet also in this talk. Okay, so why are jets interesting? So first of all, apart from the fact that they are beautiful to the eye, they are also a very efficient conveyor of energy. So basically, they can take a lot of energy from the central region of the either the galaxy or the star or whatever engine that is launching them, and dump them into huge distances away from their source. In AGN, that they can take about 10% of the rest mass energy of the matter that is accreted onto the black hole, and in gamma ray bursts it's about 1% of the mass of the black hole itself. They dump it at large distances, and when I say large distances, I outside of the galaxy even. And this energy can be used to do stuff. For example, in galaxies, we can take this energy of the jet is used to heat up the galaxy. And this sometimes leads to the shutting down of the star formation in the galaxy. So basically, an AGN is produced when some massive gravitational change is happening. It starts to swallow a lot of gas into it, and then it launches these jets, and then these jets kind of heat up the gas and then shuts off star formation in the AGNs. In gamma ray bursts, the jet has enough energy to basically blow up the entire star. Okay, so the jet is born deep inside the star. It propagates out through the envelope of the star, and as it propagates, it dumps its energy inside the envelope, and eventually this envelope can explode itself. So the jet do a lot of stuff. Another interesting thing that we think that jet is responsible is for the ultra high energy cosmic rays. So you know about the term cosmic ray. Cosmic rays are particle, mostly in high energy. These are mostly protons. At lower energy, these can be nuclei of heavier elements, and they are accelerated to very high energies. And they have different origins. And on Earth, we are able to observe these cosmic rays by different types of detectors. And we see this kind of a curve. This is the energy of a single cosmic ray, okay? And this is the flux, the number of particles per meter square per time, okay? So the most abundant cosmic rays that we see are originated from the sun. Within the sun, there are processes that accelerate these heavy elements into high energies, and some of them are hitting Earth. As you go to higher and higher energy, the flux of this cosmic ray decreases very fast at energies of about 10 to the 15 electron volts. We think that the origin are supernovas and other stuff within the galaxies, but at the very high energies, these energies, just to give you a hint of what this energy means, these particles are almost entirely composed of a single protons or that are accelerated to high energies. The energy is so high that a single proton has the energy of a tennis ball that is thrown on the field. Okay, this how high this energy is. When it hits you, it can be when a tennis ball hits you, it can be quite painful. Unfortunately, these particles are just penetrate through us. But the problem is that we have no idea what the origin of these particles. Which accelerator is so powerful to accelerate these to create such high energy particles? It is still a mystery. And one of the things that we think that can create these particles are relativistic jets. And how do we know that? So there is a very simple criterion, which is known as the Hillas criterion. And this criterion say the following: suppose that we have a particle, and a charged particle. It is gyrating within an magnetic field. So the motion of a particle within a magnetic field is a circular motion because the magnetic power is like a central power. And this, the radius of this motion is proportional to the momentum of the particle. So the larger the momentum, the larger is the radius of the particle. So as long as the particle is contained within the radius of the accelerator, I can continue to accelerate it. Once this radius, this Larmor radius, is become equal to the radius of the accelerator, then the particle escapes. This is known as the Hillas criterion, and the non-relativistic version of this Hillas criterion is used within cyclotrons. So cyclotrons are instruments that are accelerating electrons into relatively high energy to use in medical, both electrons and protons, to use in medical facilities. And basically the idea is that we have regions with only magnetic field where the particle only gyrates, and then we need, within these two regions, there is a region with an electric field where the actual acceleration is being produced. Now you can see that this electric field flips from side to side, and each time the electron is moving through this region with electric field, is getting a kick, an acceleration kick in the right direction. When the radius of the electron of the Larmor radius becomes equal to the radius of the cyclotron, it just escapes. So the system that accelerates the particle in space behaves kind of like that. It has some combination of electric and magnetic field, and it's accelerating the particles. Now, unlike in these, within these cyclotrons, within relativistic jets, this whole thing is going to be moving at a velocity which is very close to the speed of light. Okay, so in this case, when and the particle is starting will have velocities that are very close to the speed of light also. So when the particles reach velocities close to the speed of light, we can change this momentum times the speed of light to this is actually the energy of the particles, but this is the energy of the particles within the frame of the cyclotron. Remember that the cyclotron itself is moving at a Lorentz factor of gamma, so the energy that we will observe is the Lorentz factor of the cyclotron times the energy of the particles. And this is the formula that we are getting. Okay, so here we have two important things. We have the Lorentz factor and we have the radius of the size of the accelerator. So we can put that in a graph, and then we can say for different sizes of objects, of astrophysical object, what are the typical energies that we can obtain from them. And you can see that gamma ray bursts, although they are smaller than AGNs, they can reach much larger energies or much larger gyration radii because their jets are moving at fast Lorentz factor, and the most powerful accelerators are these radio galaxies. So this is how we think, why we think that that relativistic jets are part of the reason why we think that relativistic jets are powerful particle accelerator. But one of the questions that comes out of it is how can we measure the radius and the Lorentz factor? So far I told you, okay, we have jets, they are relativistic, they have huge sizes, but the question that comes, how can you tell? How do you know that these jets are relativistic? How do you know? How can you measure the radius of the thing that is accelerating these particles when these things are so far away and we do not have a direct, sometimes we cannot even directly see them. So this is what I'm going to tell you about, how to measure the radii and the Lorentz factors in relativistic jets. Okay, so let's take one step back and do some classifications of relativistic jets in AGNs. So I think that you saw this picture before. This is basically a very crude model of how an AGN, the central part of an AGN, look like. This is the black hole. This is some dusty torus that is covering around the black hole, and all the action is happening here. Okay, the sizes of these things are very, very small compared to the size of the galaxy. I'm looking at the central part of the galaxy. This is definitely not the entire galaxy. Okay, so AGNs are divided into two subgroups. One is known as radio quiet, where we have the accretion, the black hole is emitting, there is a lot of action that is happening here, but no jet is produced. And the second subgroup, which is known as radio loud AGNs, and in these subgroups we have jets that are coming out from them. The reason why we have jets here and we don't have jets here, we don't really know. We think that there is some magnetic fields that are involved in that. I can talk a little bit about that after the talk if you want to ask me, but this is not the topic of the talk. I'm going to focus on this group, on the groups of the radio loud AGNs. So even within this group, we can go further and subclassify this group, because when the jets are going in that direction, what we will see depends on where we are located. Okay? So if we are located somewhere in large angle towards the galaxy, what we will see these huge jets that are going across the sky. And then we will call this object radio galaxies. So in these radio galaxies, we are located at a large angle from the jet and we see it moving along the sky, across the sky. If we are positioned closer to the axis of the jet, we will not see this motion. In addition, what will happen is that these jets are so far that we are going to be blind by the light of the jet, and sometimes we will not be able to see the galaxy at all. Objects like that are known as quasi-stellar objects because we don't see a galaxy. All we see is this huge amount of light that is shining at a flashlight that I shine in your eyes, and then you don't see everything that is happening next to me. These are known as quasars. And when we are located even closer to the axis of the jet, we are starting to see also the high energy photons that are coming from these quasars. And then we call these groups of objects, we call them blazars, because they are even more shining even with a higher amount of light than blazars. And then quasars, sorry. And in blazars, there is some very interesting phenomena that is happening. So what this observation is showing is basically they took a radio telescope, and radio waves are very long wavelengths, so we can obtain within them a very fine, we have a much better resolution of what we see. So there are observations on Earth that are using a huge amount of dishes, of radio dishes, and these are called radio arrays. And we can pinpoint these radio arrays on the center of the galaxy, of the blazar. And what we can see is we can see blobs of that emits powerful radio emission that are coming out from these galaxies. They're moving across the sky just like a mini jet. Okay? And the interesting phenomena within these blobs is that the motion that we see is faster than the speed of light. So this is a picture that was taken on laser nodes at 3C279, and it was taken. You can't see it very well because of the projector. The first image was taken in 1992. The last image was taken in 1998. These 5 images are 6 years apart. On the x-axis, we can see the distance across the sky in light years. Because we know the distance of this galaxy, we know exactly how to translate angular distance into real distance. Okay? So initially, when the first picture was taken, this blob was about 60 light years away from the center. When the last picture was taken, this blob was about 80 light years away from the center. How many light years did it pass? What was the distance that it covered within 6 years? 20 light years. But a light year is the distance that the photon is traveling within 1 year. So how come within 6 years this blob covered a distance of 20 light years? It moves almost 4 times the speed of light. How can that be? So this phenomena is known as superluminal motion. I was told to mention that you will also have an exercise on the superluminal motion, so you better pay attention to this part. So the velocity across the superluminal motions are characterized by velocities across the sky that are larger than the speed of light. So here is a cartoon that shows you how this thing is happening. So this is the observer, the direction, this is the x direction where the observer is located. This is the center of the galaxy, and this is a blob that is moving at an angle from us, okay? And here the blob is moving, and the photon that it is ejecting, it is ejecting a photon in the x direction, in the direction of the observer. Okay? So I'm going to look at 2 photons in this exercise. The first photons was sent when the blob was close to the center of the galaxy, to the origin, and the second photons was sent when the blob reached this location. Okay? Now, the time that I see that passed between these 2 photons, I'm going to call it T observed, delta T observed, okay? And the distance between the first and second photons along the line of sight from the galaxy is just C times delta T observed. This is the actual distance, okay? So in order to measure velocities, what I want to do is I want to see what I see is a motion of the blob across the sky. This is the path that I see. This path that you see here is actually this, okay? So this path, which is the velocity of the blob times the actual time delta t times sinus theta, I want to connect it with the observed, with the distance between these two blobs, c delta t observed. So this is just a simple trigonometrical exercise. Delta t c t observed is just equal to delta c to the actual distance that the first photons covered minus the distance on the line of sight of that the blob covered before it ejected the second photon. Okay, so this is c times delta t, and this is c times delta t cosine theta, and this is equal to this distance. Okay, so the velocity that I observe, okay, is this distance, is the distance that I saw across the sky minus divided by the time that it took to pass between these 2 photons. So it's v delta t sinus theta divided by delta t observed. Now all I need to do is to place this instead of delta t observed, and I have an equation. This equation is very interesting because the value of the velocity, for velocity very close to the speed of light, I get velocities across the sky. I get perpendicular velocities that are larger than 1. The reason is that this part can be very close to 0, making the denominator larger than 1. And then when the Lorentz factor becomes very close to the peak of this curve, the maximal velocity that I can take can occur when I am looking at the object at a very particular angle. This angle is equal to 1 over the Lorentz factor of the blob. When the angle is equal to 1 over the Lorentz factor of the blob, what I see is basically the Lorentz factor itself. So the velocity across the sky that I measure is not really a velocity. It's what I think it's a velocity, but it's actually the Lorentz factor. So this is a very nice way to measure Lorentz factors of objects that are moving at superluminal velocity. And this is the reason why we know that these things are moving at relativistic velocities. Okay, so the number 4 that we saw here actually represent the Lorentz factor of this blob. I want to do a short break and to explain to you why this angle 1 over theta equal to 1 over gamma is an important angle, because it's going to, I'm going to repeat this throughout my talk. So I'm going to talk to you, to tell you about something that is known as relativistic beaming. Have you heard about it before? Okay, so what is a beaming? A beaming is basically, instead, if I have a very bad flashlight and if I have a candle and I lit it, I'm basically emitting in all directions. But if I have a very good flashlight, I can take all this energy and concentrate it in a single direction. So now the light is beamed toward one direction. And relativistic motion is basically do that. Relativistic motion is a very, very strong flashlight. Now, how does it happen? So there is, if you do this exercise of assume that you have some system that is moving at a velocity v relative to the lab frame, relative to the class, okay? And within this system is basically the blob. I'm taking particles and I'm shooting it at an angle theta from the direction of motion. So assume that this is the x-axis and I have some system that is moving in that direction, and I'm shooting a particle with an angle theta that I measure within the system that is moving. So everything that within that system, that moving system, this system I call it as, I put O tag, everything is marked with this tagged value. Now what I want to do, a second observer is located in the lab frame. This is the observer, okay? And he wants to measure this angle with respect to him. Velocity is an angle with respect to him. So in order to do that, I need to use something that is known as the Lorentz transformation, okay? And the Lorentz transformation connects the velocities from the moving frame to the velocities in the lab frame. Okay, so these equations are not very important. What is important is that from the velocity in the y and the x-axis, I can get the angle that the observer is seeing. This is the angle that the observer is seeing. Okay, and I can do another trick. And now let's say that this object that is moving at an angle theta towards the theta tag with respect to the moving system, let's assume that it's a light photon. So a photon is moving at a velocity that is equal to the speed of light, to c. So I can plug c instead of u tag here, and I get something that looks a little bit simpler. It looks something like that. Okay? And now what I can do is I can do another simplification. And now let's assume that within the moving frame, I'm actually shooting the photon exactly perpendicular. The angle now between the direction where I move and the angle of the photon is 90 degrees. Okay? So now let's assume that theta tag is equal to 90 degrees. So when theta tag is equal to 90 degrees, this becomes 1, this becomes 0, and what I get is that tangent theta is equal to 1 over gamma beta. What does it mean? Okay, so here on the top diagram, I show you how things look relative to an observer that is moving with the blob. So the observer that is moving with the blob is shooting the photon exactly perpendicular and exactly in the opposite direction. So this is 90 degrees, this is minus 90 degrees. All this thing is covering like exactly half of a hemisphere. Okay, now an observer that is sitting in the class will see this blob is moving at a velocity close to the speed of light in this direction with a Lorentz factor of gamma. The angle that this observer measures is 1 over gamma, or 1 over gamma beta, or 1 over gamma if beta is close to 1, because everything is moving at the speed of light, so beta is basically 1. So what does this 1 over gamma mean? it means that now the angle is not 90 degrees, but 1 over gamma. So this half of a hemisphere is basically focused into a cone with an opening angle of 2 gamma. And if gamma is a 10, this cone can be very, very narrow. So what I did is by moving at the velocity close to the speed of light, I took my candle, which shines over 4 pi degrees, and I concentrated the light into a cone with half an opening angle of gamma. Okay, this is called relativistic beaming because it is beaming the light. Okay, so back to the blob and the observer. Now, if this blob is moving at the Lorentz factor of gamma, the maximal angle that it can has is theta equal to 1 over gamma, because again, this is the beaming. This is where all of its energy is focused into. So I cannot see blobs that are moving at angles that are larger than 1 over gamma. And usually this is what I will see, because this statistically this is the most chance that I will see stuff at the larger, like things that are moving at different angles, I will probably see it at the maximal angle that they can move in. So usually what we will see exactly from that angle or close to that angle of 1 over gamma, and that's why the velocities that we are measuring are a good representers of the Lorentz factor. So this is all I have to tell you about superluminal velocity. So if I see stuff that are moving superluminally, I can estimate their Lorentz factor, and from estimating the Lorentz factor, I can say, okay, this thing is relativistic. But what happened if I cannot see an actual motion? What happened with these quasars or these or gamma ray bursts, for example, where I cannot see a motion? All I see is this blip that is happening and then it shuts off, and I didn't see any actual motion. Can I estimate the Lorentz factor in this case? So let's try to see what else we can do with timing of photons, because the only instrument that I have is photons, and all I can do with this photon is time them. So let's see what the timing can tell us. Let's assume that we have a system where there is, with some typical radius r, and there is an instantaneous explosion within this system. Okay, so everything is now, the entire surface of this sphere is now lit at the same time, and photons that are emitted toward the observer, leaving the edge of the sphere closest to the observer, and the part of the sphere which is exactly 90 degrees from it at the same time. So if they are leaving at the same time, they will reach the observer with some time difference, and this time difference is exactly c times this time difference is exactly the radius of the object. So far, it is a very simple problem. Now let's assume a different problem, and now let's assume that this explosion took time. It started here, and then it took some time until the wave hit this point, and then this photon was ejected. Okay? So now there is a delta t, which is, we took the explosion to happen, okay? So this photon will be emitted first, and then the second photon will follow. And now the distance between these photons, when the first photon hit the observer, is larger, okay? So c delta t observed is larger than c delta t instantaneous, meaning that this is larger than the radius of the object. So the conclusion from this experiment is that if I see a time difference between two photons that are coming from the same source, from different places on the source, and there is some time difference between them, c times delta t is an upper limit on the radius of the source. The radius of the source cannot be larger than c delta t, it can be only smaller than that. So now when we look at blazars and we look at quasars, the emission that we see coming from them is very variable. It's also a gamma ray burst. Okay, this is in jets. The object that we discussed so far were not moving. But let's assume that this object is actually this blob that we saw in this blazar, and it is ejected away from the central object. Now, as these blobs are ejected, they usually become larger under their own internal pressure and become swallowed up. Okay, and the size of these objects is usually of the order of the distance of the object from the central source. Okay, delta r, which is the radius of the object, is roughly the size of r. So this means, since we expect delta r to be of the size of r, we expect delta t, the time between two photons to arrive that were emitted from this blob, to be of the order of the time that it took the blob to reach from this location to that. Now, when we look at real objects, we can study the variability of the object. So assume that we have some object that is moving along the jet and is emitting as it's moving, and it flickers. It emits a lot of photons, and the photons are coming from different locations of these objects. And we can look at the variability of these photons, and the variability of them, this delta t, is a measure to the size of the object during the time that it was emitted. Okay? Now t is the duration of the entire flare. So if I have an object that is coming out and it is emitting, so the time that it took from the beginning of the flare to the end represent roughly the motion of the object. And as I told you before, I expect delta t to be of the order of the t, because the size of the object should be of the order of the distance it covered from the central part. What I see is I see a completely different picture. I see delta t's that are much, much smaller than t, both in blazars and in gamma ray burst. These delta t's are actually so small that the radius c delta t that is coming out of them is sometimes smaller than the size of the black hole itself. And this is something that is completely ridiculous, because I cannot have a blob that is smaller than the size of the object that launched it, especially if this object is a black hole. Okay, so how can the observed site be so small? This is the question that I want to address now. And the way to go around this, the way to solve it is, again, to understand that things are moving relativistically. Okay, so again, this very short delta t can only be explained if the object is moving relativistically, and I'm going to show it to you now. So let's assume that I'm located exactly on the direction of the motion of this blob. Okay, and let's assume that when the blob is ejected, it is emitting a photon. This is the first photon, and then the second photon is ejected when the blob is reaching a radius r from the central source. Okay, so again, the exercise is going to be similar to what we did in the superluminal velocity. This is c beta is the velocity of the blob. V delta t is the distance that the blob actually crossed within the time that I'm measuring. C delta t is the distance of the first photons, and this is the distance between these two photons. This is what I measure. This is the delta t observed. Okay, so delta t observed again is just equal to c delta t minus c beta delta t divided by c. So this is the expression that I'm getting. And when beta is very close to, when velocities are close to the speed of light, beta is close to 1, I can do approximate beta to this expression, to 1 minus half gamma squared. So all I need to do is to take that, plug it into here, and what I'm getting is that delta t is actually equal to delta t observed divided by gamma squared. So if gamma is 10, it means that the delta t that I observe is 1% of the actual delta t, meaning that the size of the object that I will measure is 1% of the actual size of the object. So that's why I'm measuring such a small object. I can do another exercise and I can look at spherical shells, okay? So assume that we have a spherical shell that is expanding, okay? And I have two photons that are emitting from that shell, similar to the exercise that we did before with the ball, okay? But before, the ball was standing, it was not moving. And because it was not moving, I could see emission that are coming from stuff that are at 90 degrees away. But if this shell is expanding, I am limited. I can only see a small part of the shell. What part of the shell will I be able to see? What angle will I be able to see? You remember the relativistic beaming? So I will only be able to see parts of the shells that are within theta that is equal to 1 over gamma from the line of sight. So I will only be able to see the front part of the shell. All this part will be completely obscure for me because the emission will be beamed away. Okay? So now the distance between these two photons is this. This is c delta t observed. Okay? And this distance, again, exactly like the exercise that we did before, is equal to r divided by c times 1 minus cosine theta. And since theta is very small, I can approximate cosine theta to this expression. And then I can plug theta equal to 1 over gamma, because this is what I see. And when I plug theta equal to 1 over gamma, I get again the same expression. So time, the observed time that I see, the observed variability of the observed delta t that I see is squeezed by a factor of gamma squared. The faster this blob is moving, the shorter the variability that I will see. And remember that I showed you these very fast variabilities in gamma ray burst. So the typical values of Lorentz factor that I'm seeing in gamma ray burst that can explain this variability are about 100. And the typical values that I see here are about 10. So this is about the size of the object. Okay? There is another very, very important factor that comes from relativistic velocities, and we call that the compactness problem. This is the third relativistic properties that I want to talk to you about. What is the compactness problem? The compactness problem comes out from the fact that the emission that we see coming from these jets, as I told you, is very high energy. Like the photons that we see, they have a typical energy of a few mega electron volt. Okay, now these photons can undergo very strange things. It's very energetic photons, when they collide with each other, if their energy is high enough, what will happen is that they will annihilate, they will disappear, and the energy within them will reappear in the form of electron pairs. So the high energy photons will disappear, and I will get pairs of electrons. The problem is that if all photons within the blob will create pairs, I will not have any high energy photons to see. Okay? So then the question that we can ask is, can these high energy photons that we see escape the blobs and reach the eye? Okay? And in order to understand, to solve this question, I want to introduce to you a physical quantity which is called optical depth. I think that you heard about it from Pasha. I will just want to tell you a little bit about it. Okay, so an optical depth represents the number of hits. So assume that we have like a pipe. And within this pipe, I have a lot of targets. And then I want to take some laser beam and I want to shoot it across the pipe. Okay? So, and I want to tell what are the chances that this laser beam will be able to exit on the other side of the pipe. So I can define a quantity which is called an optical depth. And an optical depth within this problem is representing the number of targets that this laser beam will hit on its way. And it is composed of three quantities. One quantity is the surface of each of these plates. Okay? This is the density, and this is the length that I need to cover. Okay? If tau is larger than 1, it means that statistically, each time that I will shoot the laser beam, it will hit, suppose that tau here is 10, like in this problem, tau is 1, 2, 3, 4, 5. It means that statistically, each time that I shoot a laser beam, it will hit 5 targets before it can leave, meaning that it will never be able to exit this pipe. So as long as tau is larger than 1, the chances for a laser beam to be able to exit the pipes are close to nothing. Okay, so a laser beam will not be able to leave the pipe. How is that related to our problem? Now, let's assume that the laser beam is 1 photon and the target is another photons. And these photons need to propagate within the soup of other photons. So now, the optical depth that I will calculate will tell me the number of times that these photons will interact with other photons before it can leave the blob. And if I put the numbers that I measure, the energies that I can estimate this optical depth with the radius and the energies that I see in these blobs, I'm getting a number which is with gamma ray burst, a number that is close to 10 to the 13. So in order to leave this blob, a photon is going to hit 10 to the 13 other photons before it will be able to leave the blob. Each of these hits can create a pair. So would that photon be able to leave the blob? No, because it will disappear. meaning that I have no chance of seeing high energy photons coming from it. Okay? So if I have no chance to seeing high energy photons coming from it, how come I seeing these photons? Okay? So the answer for that is lying within this parameter, which is known as F, which I called Fe. Fe is basically the fraction of the photons that can create pairs with a single photon. So let's do a little break and I will explain to you what I'm talking about. Okay? So in order to create a pair, I need to cross some threshold of energy. Okay? The energy of an electron is me times c squared, okay, which is half of mev. Okay? And in order to create a pair, in order to create two photons, I need this condition to be maintained. It means that what I need is that the energy of the first photon times the energy of the second photons will be larger than the rest mass energy of an electron square. Okay? So if I have a photon and its energy, if I have a photon, and let's assume that this is the threshold, this is the threshold energy. If I have a photon that its energy is lying below the threshold, the second photon must have an energy larger than that energy. Okay? Suppose that the first photon has an energy of 1/10 of an MeV. The second photons need to have an energy of what? 10 MeV. Okay? Because if I have, do I have a chalk here? So if my condition is that epsilon 1 times epsilon 2 is equal to me squared m to the power of 4, and epsilon 1 is equal to 0.1 me c squared, then epsilon 2 is equal to 1 over to me squared c to the power of 4 divided by epsilon 1. And this is equal to 1 divided by 0.1 times me squared c to the power of 4 divided by me c squared. And this is equal to 10 times me c to the power of 2. Okay? So the smaller the energy of the first photon, the larger the energy of the second photon. Okay? Now, the photons within this blob that I showed you before, within this blob, do not have a single energy. They actually have some sort of a spread of energies. And it is coming from the fact that these photons are created over particles that are accelerated, and particles that are accelerated are usually accelerated to a power law within the energy. So this power law that I'm showing you here basically represents the spectral distribution of the photons. I have a lot of photons with small amount of energy, and I have few photons with large amount of energy. So if I have a photon that it has an energy of exactly MEC squared, the fraction of photons that can create pairs with this one are lying here. Only photons with energy of MEC squared or larger can create pairs with these photons because of this condition. Because I need this actually to be larger or equal to me squared c to the power of 4. So if this one is exactly MEC squared, I need this one to be MEC squared or larger. Okay, so Fe basically tells me what is the fraction of photons that can produce pairs within these blobs. Okay? Now, let us assume that this blob is moving at a velocity close to the speed of light. And the typical energy that I see is half an MeV. Okay? So if it is moving toward me at the velocity close to the speed of light, at a Lorentz factor of gamma, and I see a photon with an energy of half of MeV, what is the energy of the photon inside the blob? Is it larger or smaller? So it will be smaller, because there is relativistic, what relativity is doing is taking the energy of photons that, if I'm taking a flashlight, okay, and I'm lighting it towards you. A different example. You're driving a car, okay? There is a policeman shooting a laser towards you, okay? How can the policeman measure your velocity? How does this laser gun works? Do you know? Okay, so this is something that is called the Doppler effect. Okay? Doppler effect tells you that stuff that are moving toward you, if they are transmitting sound waves, this sound wave, or light, sorry, the wavelengths are going to be shorter. Okay? So when a cup is pointing a laser toward your car, and the laser bounces from your car back to the laser gun, the wavelength that it will be reflected will be shorter than the wavelength that it was transmitted. The reason why it will be shorter, because it's now the laser is transmitted back to the cup from a car that is moving. And because of the Doppler effect, the waves are going to be shorter. So this laser gun measures the difference between waves of sound that is coming toward you from it and waves of the light that is coming back to it, and it can deduce the velocity of the car. So this is called the Doppler effect. And the Doppler effect is also a relativistic version. When stuff are moving at velocities very close to the speed of light, the wavelengths are becoming very, very short. And you know that in light, the energy of a light beam is basically proportional to the frequency. The higher the frequency, the higher the energy. Okay, so if the frequency is becoming higher, the energy is becoming higher too. And when stuff is moving at a velocity close to the speed of light, this energy is multiplied by a factor of gamma. So if I have a blob that is moving toward you at a Lorentz factor of 10, okay, and it is emitting a light with energy, a photon of light with energy of half of MeV, the energy that you will see will be 10. 10 divided by 2, 5 MeV. Okay? So it will be multiplied by a factor of gamma. And it works the other way around. If this blob is moving toward you and you see half of MeV of photons, you can say, okay, if this is if it moves with the Lorentz factor of gamma, I know that within the blob itself, the actual energy of the photon is 1 over gamma of that. So if gamma is 10, the actual energy of the photon is 1/10 of that. So the energy of the photon in this case will be the energy that we see divided by gamma. What does it mean about the energy of the other photons that can create pairs within? What it tells about that energy? That it needs to be multiplied by gamma. Okay? If I divided, this is by the way 10, sorry. No, it's 0.1, yes. If this is 1/10, if gamma is 1 over 10, if the energy of the first particle is MEC squared divided by 10, the energy of the second particle is MEC squared times 10. If the energy of the first particle is epsilon divided by gamma, the energy of the second particle should be this energy times gamma. What it means is that the fraction of photons that can create pairs with this particle just because the blob is moving toward us is now shrinking, because only these particles can create pairs. So it means that this fraction of photons is becoming smaller. It's actually becoming smaller by a huge factor, a factor of gamma minus 2 alpha. Alpha is the slope of this thing. Okay? So what it means, what I showed you now, that the relativistic motions of these blobs give me two things that can help me. first of all, the size of the object that I deduce from this delta t is now larger by a factor of gamma squared. Larger size means that the photons are less dense inside. Their density is smaller because the same number of photons is there, but they are only spread on a larger volume. Okay? A second thing is that the typical energy of the photons inside this blob is smaller. And because it is smaller, the fraction of photons that can produce pairs with that photon is much smaller as well. So the fact that my blob is larger and the energies of the photons are smaller means that my optical depth becomes smaller, because two things that will happen. First of all, the density will be smaller, and second, the number of targets that I need to pass through will become smaller. Okay? So in order to obtain, so if I want this photon to be able to exit this blob, what I want is that the optical depth will be 1, right? Because 1 means that it will undergo as much as 1 scatter on the way, and I want it to be even smaller than 1. So in order to get an optical depth of 1, I need just to plug here the correct Lorentz factor. And the Lorentz factors that I'm getting are for gamma ray bursts, as I said, about 100, and for radio galaxies about 10. So in radio galaxies, I can take these Lorentz factors that I obtain and I can compare them with the Lorentz factor that I deduce from superluminal motions, and I get something that are on the ballpark. So it is basically the same thing. So I know that the mathematics checks out. In gamma ray burst, I have no idea. Because in gamma ray burst, I do not see an actual jet. What I see is this flash of light. Okay? And from these energies, from the energy that I'm getting from this flash of light, I'm deducing that the Lorentz factor of gamma ray burst is about 100. Meaning that gamma ray burst jets are much, much, much more relativistic than AGN jets. So there is another topic that I want to tell you about. And this topic is addressing, again, the question of how do we know that DRB jets are actually jets and not something else? Okay, so all I told you is I explained to you about the compactness problem. So the compactness problem tells me that stuff are actually larger than what they appear to be. This is basically the compactness problem. Okay? In GRB, they're actually in ferrorelativistic motions, but they do not tell me that what I see is an actual jet. Because again, I could see a blob that is expanding in all directions, like a shell, a spherical shell expanding in all directions, will give me exactly the same result that I see here as jet. Okay, the compactness problem does not tell me that what I see in a jet. In AGNs, it's very simple. All I need to do is look, and I see this is a galaxy known as Centaurus A, and I see these very huge jets with these lobes at the end of the jets, and I can measure superluminal motions, I can do a lot of stuff, and I know that this is jet. This is what I see in gamma ray burst. Okay? Can you say that this thing is a jet? No, I see an explosion, and this explosion can be spherical. So how can we tell that what we see is actually a jet that is pointing toward us and not a spherical explosion? And this is the last question that I want to address in this talk. So let us assume that the explosion that we see is indeed a spherical explosion. Okay? So this is the gamma ray burst as it explodes, and let us assume that this is spherical. So I have photons that are emitted on the all 4 pi direction. And I'm sitting here. And I'm measuring the energy that is coming toward me. Now, because I am sitting in a single location, I can never know the exact amount of energy that was emitted, because all I see is what is hitting my eye here. I don't see this. All these places are located elsewhere in the universe. Okay? So I need to define a quantity that will allow me to connect what I see, the energy that I see here, to the actual energy in the explosion. And this quantity we call fluence. Fluence is basically the energy per unit area at a distance d from the source. Okay? So you know that energy is conserved, and if I have like a pulse of energy that is emitted into all direction, all the energy that left this small sphere will reach the large sphere, okay? And since the fluence is the energy divided by the surface of this sphere, divided by 4 pi d square, if I want to connect the fluence to the actual energy, all I need to do is to measure the energy per unit area that I'm measuring on Earth, multiply it by 4 pi times the distance to the object, and I will know the actual energy that was released from the object. A very easy exercise, okay? So we can actually do that. We can look at gamma ray burst, and we can measure the fluence. So the fluence that we see from gamma ray burst cover a huge range. So this is the typical fluence that we see is about 10 to the minus 6 ergs per centimeter square, and it can reach up to this huge number of 2 times 10 to the minus 4 ergs per centimeter square. I will soon tell you why this is a huge number. It looks very, very small to you, okay? The secret lies within the distance. The typical distances of that we measure from the central object to the from the location of the gamma ray burst to where we are looking are about 7 billion light years away. Okay. So the way that we know that is that we can measure the redshift of these objects. You know that. Have you heard the term redshift? You know. Okay. So the redshift is basically a distance. So I can translate this redshift into a distance, and this distance is about half the size of the universe today. So most gamma ray bursts or long gamma ray bursts are coming from distances of about half the size of the known universe. This is a huge distance. I can do the exercise that I did before, that I showed you before. I can take the fluence, multiply it by 4 times the radius square, and I get a number. And this number represents the energy of the burst if the burst was completely, if everything was emitted spherically in all 4 pi direction. The energies that I'm getting is between 10 to the 52 to about several times 10 to the 54 ergs. Just to give you a comparison what this energy means, if I'm taking the entire mass of the sun and I convert that into energy, I'm getting 2 times 10 to the 54 ergs. Now, to remind you, this event took about 10 seconds. So within 10 seconds, I need to convert the entire rest mass energy of the sun into photons, into high energy photons. And this is something that is, it's a little bit ridiculous. So I need to do something to help me. How can I reduce the actual energy in the source? What happens is that probably my translation from the fluence to the energy is wrong. What is the reason that it is wrong? Let's try to think of solutions that can reduce that energy. How can that energy be reduced? Any ideas? Remember that I don't know how much energy actually reached the other parts of this sphere. All I know is what hit my eye. So maybe what I'm seeing is not a spherical explosion, but maybe what I see is just a jet that is pointing towards me. And then all these regions that I thought that were hit by photons coming from the source, I was basically wrong. It is not, I was not correct because the jet actually covers a much smaller fraction of the surface of the sphere. Okay, so if my opening angle of the jet is about 5 degrees, okay, then the ratio between the surface of this two-sided jet to the surface of the sphere is about something like this is about several hundreds. Okay, so the actual energy is actually reduced by this fraction, theta j squared divided by 4, and I get to energy that are much, much smaller, 10 to the 49 to 10 to the 51 ergs. These are still huge energies, but these kind of energies are something that we can actually see. Okay, so the energy, the consideration of energy alone tells me that the energy that the gamma ray burst emits their energies within jets and not on a spherical direction. By the way, if they are emitting them in jets, why we see only jets that are pointing toward us? Any idea? Remember what we started with, the beaming effect? The jet is like a flashlight. The flashlight is moving and it is emitting all its energy within a cone, and its opening angle of the cone is 1 over gamma. So I will not be able to see any emission that is coming in this direction. I will only see jets that are pointing toward me. So let's look at it in another way. So again, I'm doing a different consideration now. Again, we're assuming that what we see is a spherical explosion. Okay? And each point on this explosion, now I have a shell, and this shell is expanding at a Lorentz factor of gamma. Okay? Each point of this shell is emitting isotropically within its own rest frame. But because it is moving, the emission is beamed into a cone with an opening angle of 1 over gamma. So here I'm plotting different points on this shell, and this is the location where their emission is beamed into. Okay? Now let's put an observer here. The observer will only see the points on this spherical shell where the beaming cone is pointing toward the observer. All these points in the shell, I will not be able to see them. I will only see this, and I can translate that into an observed cone, okay, with an opening angle of 1 over gamma. So all I will see from that shell is this region with an opening angle of 1 over gamma. Now let's assume that this shell is now propagating in space. And as it propagates in space, it interacts with the interstellar medium. And as it interacts with the interstellar medium, it feels pressure on it, and it starts to slow down. Okay, it's like when I'm sending, I don't know, a ripple in the ocean. The ripple starts with some velocity, and then eventually it will die out. It will start to slow down and dissipate its energy. Okay, so as this shell slows down, its Lorentz factor is decreasing. Okay, so when it decreases, I can start with a Lorentz factor of 100. After some time, the Lorentz factor drops to 50. But since I see a cone with an opening angle of 1 over gamma, it means that I will see a larger part of that shell. And as the shell continues to decelerate, I see larger and larger fraction of that shell. Okay? So what will happen is that as this shell continues to decelerate and my observed cone is increasing, the energy that I will see that coming in from it will be smaller and smaller and smaller. Okay, this stage in the burst is happening after the gamma ray burst itself. It's called the afterglow. Have you heard about the afterglow? So let's not go into it. I don't want to go into this terminology. This shell is continuing to slow down. As it is continuing to slow down, its energy is decreasing with a slower and slower rate. Now, if the shell was completely spherical, then this decrease will continue as a power law all the way until it would disappear. But if I do not have a spherical shell, but I have a part of a shell, okay? If I do not have a sphere, but I only have a small part of a shell, and this thing continues to decelerate, and my observed cone is becoming larger and larger and larger and larger, at some point, the opening angle of this observed cone will cover the entire shell. Now, if this shell will continue to decelerate, my observed cone now will be larger than the size of the shell, and I will see that I am missing light, because light from this part and that part I will not be able to see because there is nothing there. It's not a spherical shell, it's a jet. So what I will see a break in the light curve. Okay, and this break is known as a jet break because it will happen on all wavelengths at the same time because it's a geometrical thing. Okay, so when I look at this is the late light of the gamma ray burst. After the gamma ray burst itself stopped, and all I have is this moving shell that is expanding in the medium, is radiating at longer wavelength than gamma rays. Okay, what I see is stuff that are going, decreasing at some power law, and then they break. And this break is happening at the same time on all wavelengths. Because again, it's a geometrical thing. This is how I know that what I see is a jet break. I am missing light, and I'm missing light in all wavelengths, not just in a particular wavelength. And since I can time the time when this jet break occur, and if I have a model for how the Lorentz factor change with time, I can tell exactly what the opening angle of the jet is. Because at the time when the break occurred, the Lorentz factor was just 1 over theta. The cone, which is its opening angle, okay, at the time when the jet break occurs, if this is the observer, I see the entire shell. My theta is equal to 1 over gamma. And since I see the entire cone, this is the actual opening angle of the jet itself. So I can know what this is, and if I know what this is, I know the exact opening angle of the jet. So this is the trick. So the trick is to look for these breaks, understanding that they occur because as the shell continues to slow down, my observed cone is now larger than the size of the jet, so I'm missing out light, so that's why this break occurs. And at the time that this is happening, this relation is taking place. Okay? Of course, there are a lot of details here that I'm hiding. How do we know how gamma changes with time? But these are details that let's not go into them. Okay, there are a lot of uncertainties here, but the idea is the same. So when I do that and I'm looking at gamma ray burst, what I see is that the typical values of an opening angle are about 5 degrees. So the size of the jet is about 5 degrees. It is definitely not a spherical explosion. So to recap everything that I told you about today, we discussed about superluminal motions. These are blobs that we see coming from laser jets moving at velocity across the sky, which appears to be a velocity of larger than the speed of light. And I showed you that this velocity can help us understand what the Lorentz factors of these blobs are. We discussed about how variability, how the time change, the delta t that I measure between photons that are coming at different times, can help me understanding what the size of the object is. Okay? And the size of the emitting site is larger by a factor of gamma. And we also discussed the compactness problem, and I showed you that when the relativistic motions are essential for the high energy photons to get away from these blobs. The reason why they see high energy photons coming from these blobs are because the blobs are moving at velocity close to the speed of light, hence they are both bigger and the photons within them are less energetic. And that's why we are able to see these photons escaping the blobs. I showed you that gamma ray bursts are jetted, and I showed you that from 2 considerations. One consideration is the energetic, that I don't see emission coming from on the entire sphere. All I see is part of is a jet that is porting toward me. Okay? And I showed you that there is this notion that is known as jet break that happens because the beaming effect becoming weaker and weaker, and at some point I will be able to see the entire jet, and from that point on I expect to see a break. So all this consideration tells me that the jets that we see in gamma ray bursts and in AGNs are indeed relativistic. And if they are relativistic, I can translate their energy into actual energy that they are taking away from the central object. But there are many, many open questions that are regarding relativistic jets that we still don't really know. And this is an ongoing research that we're doing now. For example, one question is, what is the powering and launching mechanism of the jet? I told you that jets exist, but how do they are launched? How can I tap so much energy into such a small amount of volume? How jets maintain their integrity over long distances? If you take a spray of water or anything that is jetted and you put it into the air, at some point it will disperse. Okay, any jet of water, any fountains that you shoot water from, at some point this water reaches some point and then they will disperse. They will not last for a long time. But the jets that we see in AGNs can maintain their integrity over millions of light years. How do they do that? Why do they not fall apart? What are the particle acceleration mechanisms in the jet? I told you that the jet are very powerful accelerators and they accelerate these ultra-high energy cosmic rays, but how do they do that? We have ideas, but we don't have a definite answer to that. Are there other high energy particles that are created in jets? For example, neutrinos or very high energy photons that we see. Do they are created in jets too? We don't know that. And the last and one of the most interesting question is, can we identify the jet engine? So in AGNs, the jet engine is pretty clear. It's pretty obvious that the engine is a black hole. But in gamma ray bursts and in other stellar-sized objects that emit jets, it can also be a neutron star. And can we tell them apart? Can we differentiate between a black hole and a neutron star? We still don't know how to do that. So I will end here with these open questions, and I will open the floor for if you have other questions. Thank you.